In this lecture, we'll discuss the mechanics of a relativistic particle. We'll start with the least action principle for a free particle. So, as a reminder, in classical physics, we can start with an action functional, which is obtained by integrating the Lagrangian over time, where the Lagrangian was the difference between the kinetic and the potential energy, and then the physical trajectory is obtained by requiring that the action reaches an extremum for that trajectory. Now, if we look at the structure of this expression, so we see that here there's an integral over time. Now, in relativity, time cannot appear as a special coordinate. The time and space should enter on the same footing, so we need to work out how to generalize this principle in a covariant form. So let's think what kind of form a relativistic action can take. Now, the action has to be a Lorentz scalar. This is because the least action principle should not be frame dependent. We should be able to minimize the action in any reference frame and find the same answer. Now, also, if we use the classical action as a model, the action should look as an integral of a differential of first order. So instead of dt, we should have first order differentials corresponding to the particle's world line. Now, if we think of what is available to construct the action, the only thing that we have at our disposal for a free particle is the element of the interval along the world line, which is ds. So we have to integrate between the initial and final world points, and then there can be some coefficient here that may depend on the mass of the particle. It can contain some fundamental constants, and we can see that the constant has to be negative. So we'll put a minus sign here, and then alpha will be positive. Now, why negative? Well, recall that if we have a body that moves from world point A to point B, ds is c d tau, so we can rewrite this as the integral of dt square root 1 minus v squared over c squared from ta to tb. Now, let us evaluate this integral in the reference frame such that r a is equal to rb. So because the interval is time-like, we can pick the reference frame so that the events a and b occur at the same place. Then it's easy to see that the integral will be maximal when the particle is at rest in that reference frame. In that case, we have ta, tb, dt, and the square root turns to 1. So if the particle is at rest, we simply get c times tb minus ta in the reference frame where ra equals to rb. If the particle is moving, the integral will take a lesser value. So that means that this integral is maximized for a particle that is moving along a straight line in four-dimensional spacetime. Now, because this integral reaches a maximum and we need the least action principle, we need to put a minus sign here so that the extremum is a minimum and not a maximum. So take this expression here. And then, because it has to, when projected onto the given reference frame, that's what we do when we write it in terms of dt. So it should be L dt from Ta to Tb. We find that the Lagrangian is equal to minus alpha c square root 1 minus v squared over c squared. Now, in the limit where v over c is much less than 1, we can expand the Lagrangian to the leading order in v. So we'll find L is approximately equal to negative alpha c plus alpha v squared over 2c plus terms of order v over c to the fourth. Now, in the non-relativistic limit, we should recover our non-relativistic mechanics. So the velocity-dependent term here should correspond to the classical kinetic energy, which is mv squared over 2. So from here, we find that alpha must be equal to mc. Thus, the full definition of the action will give us minus mc integral ds. In the Lagrangian, instead of alpha, we have minus mc squared square root. Okay? Now, if we proceed according to the standard prescription, when the action is expressed in the form of an integral over time, we know what to do. The variation has already been done in the course in classical mechanics. So what we need to do is just use the Euler equation. So first, the momentum can be found by taking a derivative with respect to the velocity. Now, that derivative will give us mv divided by the square root. So this is different than classical mechanics. The square root is new. But of course, if the velocity is small compared to the speed of light, then the momentum turns into the classical formula. And because there is nothing that depends on the coordinates in the Lagrangian, then the equation of motion is simply p dot equals 0, and the particle is moving with a constant momentum as it should. Notice the action contains nothing other than the term that depends on the interval. There's no potentials here, no forces, so the particle is free to move along a straight line. Now, the energy of the particle, again, using the standard prescription, we take P dot V minus L. That becomes, so P dot V becomes mv squared, so mv squared divided by the square root. And here we have plus mc squared times the square root. So putting this together, we find mc squared divided by the square root, and that's the energy. Now, in the non-relativistic limit of small velocity, we can expand the energy in terms of v squared, so we'll find E equals mc squared plus mv squared over 2. So we have the kinetic energy, which we know should be there. It was already here. But there's also an mc squared term, which is the rest energy of the particle. Now notice that we didn't assume anything about the structure of the particle. It can be an elementary particle or a compound particle, generally any kind of body, as long as we're dealing with translational motion only. This fact will come in useful when we discuss collisions, where particles can be transformed between different types. Now, finally, both energy and momentum are unique functions of the velocity, so we can easily establish the connection between them. So if we write E squared over C squared, we'll have M squared C squared divided by 1 minus V squared over C squared, which, as can be easily checked, is the same thing as P squared plus M squared C squared. So this is the connection between E and P, and using this we can write the Hamiltonian, which is the energy expressed in terms of the momentum, as C times square root P squared plus M squared C squared. Now also we can write an expression that follows directly from comparing the expressions for the momentum here and energy here. We can write that P is equal to E over C squared times V. Sometimes can be useful. Now let's step back and observe what we have done. So we started with the action written in covariant form. So notice that this expression here is an integral of a Lorentz scalar. So it's explicitly covariant, and action is explicitly a scalar. Now then, we picked a reference frame. Notice that now we're dealing with time, and we re-expressed the action in the conventional form, which is an integral over the Lagrangian, and then we used the results of classical mechanics to derive the momentum and the energy. Now, alternatively, we could stick with the covariant formulation. So we could take this formula and proceed in fully covariant form without ever picking a particular reference frame. So this is in fact quite instructive and preferable, because keeping all expressions in covariant form can reveal some features that here are not entirely obvious. So for example, here we obtain the momentum, which is a 3-vector, as a usual 3-dimensional vector, and the energy, which is a 3-dimensional scalar. But from this expression, it's not clear whether momentum and energy are actually components of something 4-dimensional. If we stuck to the covariant form, we would never lose it, and such connections will be entirely obvious. So let's try to proceed in this way. So we come back to our action, negative MC integral ds. But now we can't use the results from classical mechanics. We have to do the job from the beginning. So what we need to do is vary the action and demand that it's equal to 0. That will give us the physical trajectory. Now this is minus mc, and then we have to vary the integral of ds. Now the variation is taken while a and b are the fixed world points, so it's the same as before. In classical mechanics, we did the same thing. We fixed the initial position at the initial time and the final position at the final time, and here that means we fixed the initial and final world points. So how do we vary this thing? Well, recall that ds squared is dx alpha contracted with itself. That means that ds is a square root of dx alpha dx alpha. Now we need to vary the trajectory, vary the world line, essentially. So what we need to evaluate is the integral of delta ds. Now don't confuse the capital S for action and lowercase s for the interval. So what is delta ds? So we need to vary this quantity here. Now, this variation will result in 2 square roots going to the denominator, and in the numerator we'll have twice dx alpha delta dx alpha. Okay, now the factor 2 cancels out, so we can drop it, and then this whole thing goes into the integral here. Now the denominator here is just ds, so let's erase this and put ds here. Now further on, remember dx alpha by ds is 1 over c u alpha. This is the forward velocity according to our definition. Now if we lower the index, we'll find dx alpha by ds here with the velocity with a lower index. So I can rewrite this as minus m, c gets cancelled, so I have integral from a to b, u sub alpha delta dx alpha. Now both variation and differential are linear operations, which means that delta of dx alpha is the same thing as d of delta x alpha. So I can again rewrite this minus m integral from a to b u alpha d delta x alpha. Now we integrate by parts. So we find minus m u alpha delta x alpha substituted at the limits, and then plus m integral from a to b delta x alpha d u alpha. Now what is du alpha? Well, we better write this in the way where du alpha is differentiated with respect to ds, because after all the trajectory can be parametrized by the interval s. So then let's substitute this here. So we have du alpha by ds times ds. Now the term with the substitution vanishes because the endpoints of the trajectory are held fixed, because delta x alpha a and delta x alpha b are both 0. So then we come back to this final term, the last term, and then delta x alpha is arbitrary. This is the variation of the trajectory. So delta s has to vanish for any delta x alpha. Now, in order for this to happen, it must be that du alpha by ds is 0 along the entire trajectory. This is the equation of motion, and the solution is u sub alpha equals constant. So the particle moves with a constant velocity. Now, let us come back. So here we have the expression for the variation of the action. So to find out the equation of motion, we assumed that the world points A and B are fixed. So this free term was set to 0, and then the requirement that the second term has to vanish for any variation of the trajectory delta x alpha leads to the equation of motion d alpha by ds equals 0. Now let's consider a different thing. So consider the variation of the action as a function of the endpoint of x alpha at point B, while considering only physical trajectories. So physical trajectories are those that obey the equation of motion, so that this is satisfied, and therefore this term is now 0. But this one isn't. So we still fix the A point, but the B point is considered to be variable. So we want to find the dependence of the action on the position of the final point on the trajectory, assuming that the trajectory is physical, meaning obeys the equation of motion. Now, clearly, from the expression that we wrote, we can write that delta S, in this sense, is equal to negative m u alpha delta x alpha at point B. We can then form a 4-vector we can call delta S over delta x alpha. We can call it a 4-vector. It's obviously a 4-vector. S is a scalar, and you differentiate with respect to the components of a contravariant vector. So this gives us negative mu sub alpha. It is a covariant vector. Now, it's nothing other than the 4 velocity times mass. But we can call it p sub alpha. And we can identify it as a 4-vector that contains in itself both the energy and the momentum of the particle. So to see that, first we can recall that in classical physics, we've learned that the derivative of the action with respect to the position of the final point on the trajectory, considering only physical trajectories, is just the momentum of the particle. Now, the derivative with respect to the time of the final point is negative energy. You can come back to your class in classical mechanics and recall these facts. Now, the derivatives here with respect to delta x alpha are just the derivatives with respect to Ct and with respect to r. So it's the same thing as here. So we can simply write down the components of this vector by inserting these equations into here. So for the time-like component, this will give us negative E over C. It's a derivative with respect to Ct. So there's a C there. And the derivative with respect to B, with respect to RB, is just P. Now here it's x alpha B here. Okay? Now from here it follows that P alpha is just E over C minus P. Now these are a covariant components of a 4 vector, so the contravariant components are just E over C and P. So the energy and momentum form part of one single 4 vector. Now, this is consistent with what we found before by projecting onto a given reference frame and using our knowledge from the representation through Lagrangian. So remember, we found before that the momentum that follows from the Lagrangian looked like that, and the energy was mc squared over square root 1 minus v squared over c squared. Now, if we insert this into this expression, so we would find the 4 vector that looks like mc over square root, and the space-like component is mv over the square root. But this is indeed exactly mu alpha. Recall the definition of u alpha. Time-like component c over the square root, space-like component v over the square root. So multiply by m, like here, and we get the 4 momentum. So this momentum for a vector is exactly what we should have expected to find. Now, the relation between the energy and momentum that we found before can be written as p sub alpha p super alpha equals m squared c squared. Notice that because energy and momentum are time-like and space-like components of a single 4 vector, that means that under Lorentz boosts they mix with each other. So there is a transformation that involves energy and momentum under boosts that gives you E prime and P prime in terms of E and P. Now also note that we can directly use the results from classical physics that tell us that energy and momentum of a closed system are conserved. We can use this knowledge, for example, to analyze collision problems. So let's consider an example of a collision problem. Let us find a reaction threshold for the production of a proton-antiproton pair in a proton collision. So let's assume we have 2 particles, a proton and another proton. And one proton is at rest in the lab frame, it's just a target, and the other proton is incident with some momentum and energy. They are obviously related through the energy-momentum relation. And the question is to find the minimal energy of the incident proton that would allow the reaction that produces a proton-antiproton pair. Now, to avoid confusion, P will stand for a proton when it has no indices, but momentum will have either an arrow on top of it for 3-dimensional momentum or a subscript or superscript alpha when it's a 4 momentum vector. So the trick here is to judiciously choose the reference frames we're working with. So let's first realize what is the condition for the reaction threshold. For the minimal energy of the incident proton, what should we expect to see in the center of mass frame? So the condition for the threshold, if you think about it, all 4 particles after the reaction should be at rest in the center of mass frame. So that minimizes the energy that the 4 particles have, because otherwise you would have to add kinetic energy. Now, the 4 particles can be at rest in the center of mass because it's center of mass. You can't use this condition in the lab frame because of momentum conservation. But in center of mass, this is exactly what we expect to find. Now, in the lab frame, all the 4 particles would just be moving along together. So here's how we can find the threshold. So first, let's write the momentum, the 4 momentum vector, in the center of mass frame and in the lab frame. You'll see why this is convenient. So in the center of mass frame, we can write the 4 momentum vector. So call it P prime, because it's center of mass frame. We'll use a prime to designate it. We'll write it after the reaction has occurred. Now, we have 4 particles at rest instead of a mass frame. So we have 4 rest masses, or 4 rest energies of a proton divided by c. So the rest energy is mc squared. So here I have 4 mc. Now the momentum is 0. They're all at rest. In the lab frame, we call it P alpha. We will write it before the collision. We have only 2 particles before the collision. So one of them has energy E over c. That's the incident proton. And then the proton at rest has energy mc squared. Now the momentum of the incident proton is p. So this is before the collision. Now p alpha and p prime alpha are different because they're measured in different reference frames. But what we can use is the fact that the contraction of p alpha with itself is frame independent. It's a scalar, so it has to be the same in any reference frame. So I can write it in the lab frame or in center of mass frame. Now we also know that p alpha before the collision is equal to p alpha after the collision, and same thing for p prime. So I can combine these two and use both momentum conservation and the Lorentz invariance to write that p alpha before is equal to p prime alpha after. So now all I need to do is write the squares of these 2 momenta and equate them to each other. So the left-hand side, before the collision in the lab frame, I can write E plus mc squared over c squared minus p squared. And then the right-hand side is just 4mc squared. So I use the rule for calculating the square of a 4 vector. You take the time-like component squared minus the sum of squares of the space-like components. Now, of course, p here, the momentum of the incident proton, is related to its energy through the relation E squared equals p squared c squared plus m squared c to the 4th. So let's solve this equation. Let's open the brackets on the left. E squared over c squared plus 2em plus m squared c squared minus p squared equals 16 m squared c squared. Now we can combine this term with minus p squared using this relation. That will give us m squared c squared. So on the left we have 2em plus 2m squared c squared equals 16 m squared c squared. Now take 2m squared c squared to the right. This makes 14 m squared c squared, or E equals 7 mc squared. That is the energy of the incident proton. Now, if we want the kinetic energy, we just subtract the rest energy, and that becomes 6 mc squared. That's the kinetic energy at the threshold. Now, the rest mass of a proton is approximately a gigaelectron volt. So the threshold kinetic energy is approximately 6 gigaelectron volts. Finding a reaction threshold is a common problem, and it's useful to know this trick where you take the form momentum measured in the lab frame before the collision and the momentum in the center of mass frame after the collision. This concludes this lecture on the relativistic mechanics. We worked out the equation of motion for a free particle and the generalization of the energy and momentum to the relativistic case. And we saw an example of how energy and momentum conservation can be used to find a reaction threshold.